And here we are, the last section of chapter 12. We are going to look at similar and congruent solids. This lesson will be a lot like the last lesson in chapter 11. So if you need to go back and maybe refresh on that, that might be a good idea. But we'll go through everything you need to know in this video too. So similar solids have the same shape, but not necessarily the same size. And just like when we talked about similar polygons before, they need to have the same ratio. For congruent, congruent's going to have everything about them be the same. So I'm going to write the ratio is 1 to 1. So same height, same base, same angles, everything about them's the same. So the questions, some of the questions are going to say determine whether they're similar, congruent, or neither. If they're similar, give the scale factor. Well, for this first one here, they just give us 2 of the dimensions. These are regular pyramids, so you know that like this is 8 and this would be 12 because that's the way we've practiced them. So I'm going to check and see if these have the same ratio. So the ratio of their heights is 4 to 6, which is the same thing as 2/3, or when we did this before, if you'd rather divide them, that'll be the same thing. We want to see, is that equal to 8/12? Well, if you divide each of those by 4, you get 2/3 also. So these would be similar, and this would be the scale factor. The scale factor would be 2/3 from this first one to the second one. That's usually the way I write it. The book is kind of vague, so if you said 3 to 2, I would also accept that as correct. For this next one, because they have all 3 dimensions here, you need to make sure you're checking all 3. We want to see, is 2.5, that corresponds to 1.5. Is that the same thing as 3 to 1.7? And is that the same thing as 6.2 to 3.4? So you could do some like complex cross multiplying. I think what I would do is just type it into my calculator. 2.5 over 1.5. You get 1.6 repeating, or if you'd rather have it as a decimal, 5/3. If you try these with the other ones, you do not get that same decimal. This one here would round to be 1.76. It's kind of close, but you could just stop here. These would be neither. And hopefully you can tell if they're congruent, just all of the dimensions would be the same. When we're looking at the ratios, the ratio for scale factor I'm going to write is A to B. We've done this for the ratio of areas. Surface areas works the same way. The ratio of the areas or surface areas, you can't just use the same ratio. What you do is you square each part. So reference back the notes from 11.5 if you need a refresher on that. So if area, you square each part. Volume, think of that as cubing each part. So some of the questions are going to ask you to kind of go back and forth between these 3 different parts. Just pay attention to whether you're squaring, or maybe you have to take the square root, cubing, or taking the cubic root. And if you need to know how to do that on your calculator, I'll show you that in a little bit. So for this one here, the scale factor, I like to go from left to right. So I'd say that the scale factor is 3 to 2, but again, it doesn't say here, so if you said 2 to 3, that would also be fine. The ratio of their surface areas would be 3 squared to 2 squared, which then is 9 to 4. For volumes, it'd be 3 cubed and 2 cubed. So 3 times 3 is 9, times another 3 is 27, and then 2 to the third power is 8. So that would be what you'd have to write in a proportion if you had to look at some examples of this. Here are some examples. This first one says you have two similar cones. It gives you the radii. Because it tells you that they're similar, you know that the ratio is 9 to 12. And then I go ahead and simplify that whenever I can. The ratio is 3 to 4. This first part is asking what is the ratio of the surface areas of the smaller cone to the larger. Well, this is the ratio of the sides, or of the radii. So think of that as being like a singular unit length. So that's, inches to inches. Those are singular units. To go to area, you need to square each part of that. So the ratio of the surface areas would be 9 to 16. And then the ratio of the volumes, you would have 3 cubed to 4 cubed. So 3 cubed is 27, and 4 times 4 times 4 is 64. So this would be the answer to surface area ratio, and this 27 to 64 is the ratio of their volumes. You can also use this to answer different questions about it. They don't give you the radius here. I have had students that use the volume and the height to find the radius, and then they'll use the same type of thing here. I would not recommend that. Here's how I would do this one. They give you the volumes. These are the volumes. I would simplify this first. This is the ratio of the volumes. And simplifying this is maybe easier than what it looks. The pi and the pi will cancel out. I would go ahead and cross off those zeros, dividing each by 10. The ratio of the volumes is 27 to 64. When you're doing this then, and you want to go back to the ratio of a singular length, like the ratio of these heights, you're going to take the cube root of both of these. And I'll turn on the document camera and show you how to do this just in case you don't know. On a calculator like mine, you have to push the number 3, and then it's second the caret button gives you this little like x root. What this is saying is it's saying put the 3 in place of x, so this would be cube root. So if you wanted to do like the cube root of 27, that would equal 3. Or the cube root of 64, that's 4. Or you could even do the cube root, the cube root of 200, and then that would be like the decimal approximation for what that would be. So what you get here is you get 3 to 4. This is the ratio of sides, or the radius, or in this case, the height, the scale factor between these two cylinders. So the scale factor is 3 to 4. I can set that up with the h and the 10, and then I can cross multiply and solve this. So 4h equals 30. 30, when you divide it by 4, you get 7.5. So the height would be 7.5 inches. And then for this last example here, it gives us these softballs are similar spheres. If the radius of the larger softball is 1.9, find the radius of the smaller softball. Same type of example as the last one. We have the ratio for volume. What I would do is I would simplify 9.15. I would divide it by 4.06. And this here doesn't work out to be like a nice fraction. It's something pretty big. What you can do is you can, if you want, take the cube root of all of it, or you can do those as two separate parts. I've had students like to do this both ways. If you do it as two separate parts, again, it doesn't work out very nice. This top number is 9.7082, and the denominator is 7.4047. This is your ratio. If you don't want to write that as a ratio, you don't have to. You could just get like one number there, but I think most of the time students like to have this as a proportion, so then they can cross multiply at the end. So when I take this and cross multiply, you should be typing this into your calculator too. Make sure you're getting the answer. This is about 1.45, and that would be inches. So you guys will practice this. If they happen to have given you surface area, then instead of doing cube root, you would have done square root, and just make sure you're going between those using the correct form of root.